Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what is up, good TWIML people? As many, if not most of us passed the 100-day mark of shelter in place, work from home, and other quarantine measures, I want to both extend to you my best wishes for your health and happiness, and also to remind you to not let your guard down. COVID-19 is serious business, and you don't want to get it or give it. Be sure to wear that mask when you'll be around other people, avoid indoor crowds, and limit your exposure by minimizing the time and maximizing the distance when you're in contact with others. Before we jump into today's show from our CVPR series, I'd like to share a few quick details about the next great event in our continuing live discussion series. Join us on Wednesday, July 1st for the Great Machine Learning Language Undebate, as we explore the strengths, weaknesses, and approaches of both popular and emerging programming languages for machine learning. We'll have great speakers representing Python, R, Swift, Clojure, Scala, Julia, and more. The session kicks off at 11 a.m. Pacific time on the 1st, and you won't want to miss it, so head over to twimlai.com/languages to get registered. At this point, I'd like to send a huge thank you to our friends at Qualcomm for their support of this podcast and their sponsorship of our CVPR series. Qualcomm AI Research is dedicated to advancing AI to make its core capabilities, perception, reasoning, and action, ubiquitous across devices. Their work makes it possible for billions of users around the world to have AI-enhanced experiences on Qualcomm Technologies-powered devices. To learn more about Qualcomm and what they're up to on the AI research front, visit twimlai.com/Qualcomm. And now, on to the show. All right, everyone, I am here with Pavan Turaga. Pavan is jointly appointed in the schools of electrical engineering and arts, media, and engineering at Arizona State University. Pavan, welcome to the TWIML AI podcast.
Thank you, Sam. It's a pleasure and an honor to be here. Thank you.
It is my pleasure to host you here. I'm looking forward to digging into your paper that will be presented at CVPR, Revisiting Invariants with Geometry and Deep Learning. But before we do that, I'd love for you to share a little bit about your background and how you came to work in computer vision and ML.
Sounds great. So my beginnings in this area started as a senior in my undergraduate years. I was looking at problems like face recognition, face tracking from video, trying to do a senior design project, really. And as I started digging more, this was in the early 2000s. And it was a very exciting time to be in the field of computer vision because the problem statement in those days would be presented as giving a computer the ability to see. And that felt like, wow, that's a frontier topic, right?
Yeah.
And I said, looks like I'm sufficiently invested in this. Looks like it intersects with things like neuroscience, perception. There is interesting mathematics. There is interesting computing happening. Very highly interdisciplinary, and it felt like there was much work to be done. So I decided to go to school in grad school in 2004 to the University of Maryland, studying with Professor Ramachalappa, who is a pioneer in this field and very well known for face recognition techniques and a lot of interesting things in vision at the time. And as I started my work in the lab, I broadened from just face recognition to other things like understanding video, understanding time series, understanding the role of light, geometry, illumination, reflectance, all these physics-based concepts and how they interface with pattern recognition methods or machine learning methods. And as I went deeper and deeper into it, I felt like there was a big disconnect between the methods of physics of image formation and the methods that are used in machine learning, where it's just pure data-driven and statistical techniques. And I was trying to find some middle ground where I could inject physical knowledge into certain structures that could blend well with machine learning techniques. And one thing led to another. I started getting interested in this area of mathematics called Riemannian geometry and then topology as a means to express these intuitions and these constraints from physics and interface them with machine learning before deep learning. So that's the theme of my work over the past decade, which is try to understand basic phenomena, whether it's images or video or human activity. And in recent years, we've also broadened our investigation beyond computer vision to include things like wearable devices and physiological monitoring, where the phenomena under study is basic human movement and other things. Try to understand it from first principles and try to express that knowledge in a way that constrains, conditions machine learning. So that's the general intersection of topics I've been looking at.
Okay. And I mentioned in introducing you that one of your appointments is with a school that has arts in the title.
Mhm.
Are how does that come up in your work and research? Or
So
are you particularly, connected to that particular piece of that school?
So that's a whole story by itself. And I can go very organically about how it all began, or I can go in hindsight, this is how it went. So organically, this is how it began. Our school was founded in 2009, and I graduated from my grad school in 2009. But then that was 2009, very similar to 2020, Wall Street collapsing and
Yeah.
breaking loose. So I stayed back for a postdoc for a couple of years, and when I went interviewing in 2011, this position opened up in this school under the title of assistant professor in human activity analysis.
Huh.
It was very intriguing, and I had been doing human activity analysis as far as understanding video-based gait analysis
Okay.
was concerned.
Calls to mind like fitness trackers and quantified self and all that kind of stuff.
Right. So this was a little before all that stuff happened in popular
Okay.
culture. And I came and I visited, and there was a mind-boggling sense of interdisciplinarity that I saw in the school. People in music looking at stuff like that, right? Accelerometers, wearables, driving, interactive performance with it. There was a group doing stroke rehabilitation where you would track human movement through motion capture and sonify the qualities of your movement. So smoothness or jerkiness would be converted to sound, and you can hear yourself, and that provided additional feedback for you to correct your movements.
Oh, wow.
So it was a very mind-blowing experience, and even now people find it very intriguing when I mention these things. So the human activity analysis component was a way for the school to address slightly more formal ways to think about human movement, whether it's sensed from a camera, whether it's sensed from a wearable device, whether it's motion capture. Try to come up with techniques to represent human movement and then do machine learning on it, or feed into these other applications. And it seemed like I was the right fit at the time, and I got the job. And I've been here for 8 years, and it has led me into very interesting collaborations with media artists and health scientists who are interested in the intersection of computing, art, and things like health promotion. So that's the other side.
You mentioned that one of the big themes of your work has been integrating physics-based principles and computer vision. Can you maybe talk a little bit about that in the broader context of the computer vision landscape? We've talked about this quite a bit on the podcast, and I kind of describe it as a pendulum that's kind of swung from physics-based models to statistical and kind of is settling somewhere in the middle now. But it sounds like you've been working at this for a while. I'm curious how you think of it.
Yes, I mean, you're absolutely right. It's been a pendulum that keeps swinging, and I don't think it settles anywhere. I mean, that's the interesting part about about computer vision. Every time
And
someone thinks
pendulum, I
it's
guess.
settled, right, everybody thinks it's settled now, and then soon it shifts. So, I mean, yes, it's been going on and off. This idea about, I mean, I like to think of it as model-based vision versus purely data-driven, methods of thinking of vision.
Yeah.
Uh, the way the pendulum swings, in my opinion, is not that the problems are changing. It's just the language that goes into talking about it and the tools that go into addressing it.
Mm-hmm.
Those keep shifting, but the problems have remained mostly the same. And the problems are the following, in my opinion. Uh, so vision is a very unique some people think of it as an application of machine learning, which is a reductionistic way to think about it. Sure, everything is data and everything is fed into a model and out comes a decision. But vision and any perceptual, field of inquiry, that can include vision, sound, haptics, any of these things which have to do with perception, I feel are fundamentally different than any other application of data analysis. The way we perceive the world is not the way, let's say, bank transactions are processed by a machine learning computer, machine learning technique. There is a huge amount of variability, is the way I'd call it, that exhibits in the natural world, which is somehow either discarded or properly parsed out by whatever's happening in our brains. And the sources of variability are physics based to a large extent. The same picture under a different lighting condition looks different. The same picture under a different, slightly changed viewpoint looks different. So that looking different part is what gives rise to statistical variability. And the statistical ways of thinking are, well, let's just fill up the observation space with more data points and we'll figure out what the shape of the distribution is from data, which is okay. In as n tends to infinity, I guess that's fine. But when n doesn't,
data augmentation approaches and domain adaptation and that kind of thing.
yep. But under n not tending to infinity, if you only have a few data samples, you are better off trying to understand how the physics around you affects the observed imagery. And that's where I think the methods have shifted. So, in the keynote that I have at CVPR, at the workshop called Differential Geometry and Computer Vision, I go through some of these historical trends. And one of the core themes that brings it all together, the word that I use is called invariance, which is when you look around and try to classify objects, we are able to do this in a way that is invariant to a lot of nuisance variables. That is light, shading, viewpoint, and all sorts of interesting effects that are hard to describe. When you say invariance, there's two ways to think about it. The physics-based ways to think about it are, let's say I am looking at this scene, I know everything about this scene, including its 3D geometry, including how the paint reflects off light, including the wavelengths in the incoming radiation. If I have full knowledge of all of this, then I can re-render a scene. Let's say I can, just like how it happens in graphics, I can create so many different versions of the same picture if I had full knowledge of everything, simply through a forward rendering process and construct variability. The data-driven ways of thinking about it say, if you don't have access to everything that you need to understand the phenomena, what is the minimal set? What is the minimal piece of information that is needed to get a job done? And that's the dichotomy in the physics-based ways of thinking and the statistical ways of thinking.
So when you use this term invariant, is the invariant referring to, say we're talking about a scene with an object in it that might render differently in different lighting conditions, et cetera. Is the invariant that object that is definitively in the scene, and then we've got all these other effects, or does the invariant refer to something else, maybe something more on the mathematical, from a mathematical perspective?
I mean, the word invariant, of course, will depend upon what the end task is. If it is object recognition, yes, something intrinsic to the object is the invariant.
Okay.
It is not always as simple as saying the invariant is the color of the object, because that changes. It is often not the same as saying the invariant is the edge map of the object or certain corners of the object, because they go in and out of view. So there's not easy ways of describing what that invariant actually physically means. So it becomes mathematical at some level. There is no linguistic equivalent that I can come up with. But if you look at this rendering ways of thinking, if you can render this object that you're interested to recognize in all possible viewing conditions, all possible lighting conditions, and you have this huge set of pictures, that huge set of pictures could be called, the word sometimes that gets used is equivalence class, or sometimes they call it an orbit. So this object that you're trying to recognize manifests itself in all these different ways. If you have a handle on that set, you are in good shape. If you have a different object and you place it in the same scene and you render it in all these different variations and you have its own different set, then the invariant that separates these two is some measure of difference between these two sets of pictures.
Mm-hmm.
And sometimes that set of pictures can have a nice structure, which can allow you to compute it in closed form, and sometimes not. So the way we have been trying to express, sometimes illumination is complicated. And if in the most general case, we don't know how to describe this full set of pictures under some simplifying assumptions, which is rooted in some old work from the 90s. Bellhumer and Kriegman wrote a very famous paper. They said, what is the set of all faces under any given illumination condition? And they made some simplifying assumptions of what a face is. I mean, if I ask you define a face, it's hard to mathematically define a face, right? So how do you even
I
begin?
mean, and this is why we've tended towards, deep learning and
Right.
statistical methods over the past few years, because we don't know how to define these things.
Right. So exactly. But here is what they found. They said if you define it in some sub-linguistic ways, let's say it's a convex object, and let's say it's an object which has reflectance defined by some Lambertian properties, then you can actually write down what the set looks like. Now comes deep learning, which says I can define these things, give me data. And the more data you have, the better it is. But no one knows how much data is enough, right? I mean, the more is better is the answer, but how much is enough is never known. And we have been positioning ourselves at that intersection where we say, look, if I know that I'm looking at faces, I'm going to weaken the structure a little bit. I'm going to say that, yeah, these objects that we're looking at have some characterization under these assumptions of simplicity. But then comes deep learning, which allows me to fit those other degrees which I'm not able to specify analytically. So we're trying to reduce the need for larger and larger training sets by restricting the deep net layers somehow that are motivated by the knowledge of that physics of image formation. Sure, we don't know how much data we need to get the full specification, but we're saying this will reduce the need for more and more data. And all things being the same, with the same amount of training sets, the same complexity of the deep architecture, adding these constraints known from the physics of image formation improves performance. And it also stabilizes performance against degradation of inputs. Typically, if you blur a picture, if you re-render a picture in slightly different ways, performance drops pretty dramatically. We are able to avoid that. It's a middle ground, I'd say. We are not being super specific about defining objects, nor are we saying more data is good. We are saying something in the middle. That is, we are trying to come up with some description of that equivalence class under simplifying assumptions, and then let data fill in the rest. So that's the way we're trying to marry the two things.
And is the result a mathematical analysis in closed form, or is it experimental results on data sets?
It's both.
Okay.
Yeah. Most of the things we do is we end up having constraints, which are closed form mathematical equations.
Mm-hmm.
Maybe one layer in the deep net is expected to be orthonormal because the physics of image formation says that certain variables under certain lighting conditions will have an orthonormal structure. Okay, that's the way we impose the constraint, that certain layers might have an orthonormal constraint put in. But then the network itself has to be learned end to end with data sets.
Mm-hmm.
And the performance has to be validated empirically on data sets.
Okay.
One of the interesting things we found is this concept of orthonormality, which seems to have some very special power. What we're finding is whether, think of it. So we played with this idea in a paper for BMVC last year, where we took some classic, disentangling autoencoder kind of networks, and we had good reason to impose an orthonormality constraint on the latent blocks of these disentangling autoencoders.
Mm-hmm.
By orthonormality, we had to write up a whole, theory around we expect these factors to represent either movement or lighting conditions or deformations, and under appropriate relaxations, they all become orthogonal to each other and they all have the spherical structures. So looking at all of this, it looks like orthonormality is a trade-off, which is coming close to what the physics is telling us to do, and but also being sensitive to the idea that it has to be implemented easily. We don't want to overcomplicate things, and we want our constraints to be differentiable. So it's a design process. So we threw in these orthonormality constraints on disentangling autoencoders, and boom, the numbers of disentangling quality just went up quite significantly.
And so in the case of an autoencoder or on the layer of a deep network, what does it mean to impose that kind of constraint? Is it, um, architectural, and does it mean that you're diverging from kind of your CNN, ResNet kind of tried and true architectures, or is it, loss function based or something totally different? How do you impose those constraints?
There's two or three ways in which it's happened. One is we stick with architectures as is, don't mess with the architectures, but add in loss functions.
Okay.
That works when the constraints are actually expressible as a closed form equation, like spherical losses or orthonormality. Those can be written down as a closed form equation. Sometimes the constraints we arrive at do not have an equation, but they have what is called a manifold structure. And why manifolds arise is very closely related to invariance. Here is an example. If I say, so the idea of invariance is this, right? I mean, you have a feature space. Let's say the feature space is something. You have this feature space in Rn, and
Be more specific than something so it's easier to follow.
so let's say it's the latent space of AlexNet. Okay, some features drawn from the latent space of AlexNet, which is embedded in Rn, right? So it's a vector in Rn.
Yep.
And then we come in and we say, look, I want to impose a slight equivalence here, which is if I rotate my picture, looks like the features are also changing somehow. I mean, the features are not always invariant to physical variables like this, right?
Mm-hmm.
But if you're able to say that this feature, this feature, this feature in Rn actually represent the same picture, just that they're rotated, we are trying to basically paste the features and thereby the underlying space into something else to express that concept of equivalence. And sometimes when that ways of expressing these equivalences is well defined, what happens is the space gets crumpled. You hope that the neural net learns to crumple the space all of its own. That is one of the overarching hopes in deep learning, that as you go through the layers of deep learning, the deep learning is learning to squish and crumple the original feature space into interesting ways to get a job done. But what it's doing is it's not always getting the job done the right way because you never have enough data. But if I explicitly tell it that here is how rotation affects the features, and here is how you paste them together through whatever mathematics that's needed, then we get some manifold structures. This crumpling can sometimes be expressed as a manifold. If you want to say in the concept of in the paradigm of loss functions, how do you express a manifold as a loss function? Sometimes you cannot.
Mm-hmm.
What you can do instead is, manifolds are basically crumpled spaces, and they have ideas associated with them, which are analogous to how we think of maps. And the Earth itself is composed of the Earth is a manifold, but then it's also a sphere approximately. So if you forget the idea that it's a sphere, but if it were a general weirdly shaped blob, you would represent it by a series of charts, and you would explain how the charts connect. And that's the way you specify a manifold, through things called charts. And charts are also sometimes, they have a thing which is similar called tangent spaces. So you sort of flatten the manifold in local coordinate charts, and you can express that tangent space as a vector space. So once in a while, we have run into these conditions where we have a constraint which was expressed as a manifold, which could not be written down as an equation, but whose tangent space could be written down. So we were able to enforce conditions of that tangency and said, I want this layer in my deep net to represent coordinates of a manifold on a specific tangent space. And the mapping from that back to the manifold could be written down in closed form. So it depends.
All right, let me see if I can up level this anywhere close to what you just said. What the way I'm kind of hearing this is that you've got some problem, say you've got some object and you apply some simple transformation to that object, maybe you rotate it.
Right.
If you've got a deep neural network that is trying to detect that object, for example, and you've trained it there may be some feature space or some representation of that object in the different layers of the neural net. In a oversimplified world, you'd kind of want there to be a relationship between the rotation of the object itself and the rotation of the features. Like maybe you could apply some simple transformation of the features, but the world isn't, networks aren't that simple. But it turns out there is a relationship between the features. It's just more like this crumbly manifold thing. And you found a way to, express that using the mathematical language of these manifolds that allow you to detect the actual invariance of the object.
That is very correct. Thank you for giving me those lines. The only disclaimer is we have been able to do this for a few common sources of physical variability, and that includes things like rotations of objects and deformations of moving parts in certain cases,
Okay.
and lighting conditions under, just to be very clear, we haven't been able to do this across the board for every possible thing we can do.
Right. So simple, like, maybe not 3-point studio lighting, but a simple light source
Right.
and a simple, radial rotation or something like that. But,
Right.
Clearly there's lots of things you can do in the physical world that aren't amenable to that representation.
Absolutely. Yes.
Okay.
Yes.
Okay, cool. And so one of the things that comes to mind in thinking about this, in your work, you kind of fall back on, or maybe ground yourself in, what you call pragmatic choices of deep architectures, meaning kind of the popular stuff, the way we're doing things today.
Mhm.
But I think of, like Jeff Hinton's Capsule Networks is trying to come at some of the same ideas or same problems. Are you familiar with that work,
Yeah.
and you compare contrast?
I mean, we've tracked that body of work also. Again, he's, with all due respect, ACM Turing Award winner. I can't answer that easily, but my take on that is it's an overcomplication. I mean,
Okay.
it's ignoring so much. It's ignoring the basic laws of rotations are not that hard if you understand how to express rotations, and taking out that invariances is doable without that level of complication. So
I'm correct that you're trying to come at some of the same problems, at least.
right,
Okay.
it may be the case that if that enterprise succeeds, if that capsule network enterprise succeeds, it may be a more general solution
Mhm.
to everything, maybe. But but if you want to be a bit specific about understood factors of variation, I feel that's an overcomplication, and there are nicer ways to do that, and I think we're able to do that in a better way. Yeah.
So you've developed this approach, and you mentioned that you've got some experimental results as well. Can you talk a little bit about how you frame the question experimentally and what you've seen?
Sure. I think, I mean, the way we frame it is we want to keep a few things fixed. And the way we keep a few things fixed is we say, pick an architecture first. And that can be AlexNet. It can be, we're looking at things like DenseNet, PointNet, all those, architectures which are known to work well for certain databases. Keep the architecture more or less fixed.
Mhm.
Keep the training set more or less fixed. The only thing that varies is, don't play too much with new, fancier data augmentation methods. The only thing we are doing is adding in constraints, either in some latent variables or we're adding in certain augmented loss functions. So most of the additional thing that we're doing is a mathematical expression of some kind, and keeping in, otherwise it's hard to compare. I mean, if you say, let me train it for more iterations but not add a constraint, can you compare it? So keeping mostly the computational resources fixed, we are asking if this additional mathematical knowledge pushes the envelope. And we've been finding that it does. We have done that for image classification. We've done that for disentangling networks. We've done that for time series problems recently. And some of our compelling results are indeed from time series modeling, where we've applied this to human activity recognition data sets with either stick figures or wearable devices.
Mhm.
And the kind of factor that we are trying to factor out in human movement is not light and shape and geometry, but it's time series variability issues, which is the same action when performed by the same person but at a slightly different time will give rise to slightly different traces because people have intrinsic variabilities in how they move. And oftentimes that variability gets expressed through some time warping kinds of relationships. what we've done is express the time warping property as a constraint, which can be forced by the network to be factored out in a latent variable if we just throw in that constraint in the loss function. And we found that it improves numbers significantly just like that, without any additional training, without any additional data requirements.
So
So
some of the pictures, or what I think are the pictures of this, uh, if I'm understanding the problem is along the lines of, start from your seat in the living room, go to the refrigerator, grab a drink, take off the cover and drop the cover in the trash can, and you've got this kind of two-dimensional plot of the path that the person might take in doing all that. And your argument is that the path is an invariant because the task is the same. It's, do X and Y, and what you're trying to do is identify. Well, what is the fundamental? Is it identifying the path? Is it somehow in a data set with lots of these, traces or paths, identify which ones correspond to the same
right.
actions? Or
It's close. I mean, we haven't looked at paths in that way, but we've looked at traces of stick figures. So you have like 50 joints being tracked, and you have the full time series of 50 joints evolving in space and in 3 dimensions. That comes from motion capture, say.
okay,
And yes, they are actions not very unlike what you're saying. Actions in a kitchen, actions in a room, actions in an office, picking up objects, placing them here and there. And the feature that is invariant, of course, is hard to linguistically describe, but one of the variables that gives rise to confusion is that people sometimes take longer to do the same thing. People sometimes are
mhm,
fast in certain phases of the movement, slow in certain phases of the movement,
right.
or there is asymmetry in the body. The left arm swings more than the right arm. There's all these interesting sources of variability which are hard to, and the only way deep learning will be robust to that is if you augment it with all these variables, all these sources of variation. The way we think of it is that the variability here is expressible as a warping of the time axis, whether it's short versus long, or speeding up versus slowing down, or if it's one side faster than the other side, or the swings are smaller than the other. It's all a time warp. Sometimes it can be constant, sometimes it can be non-constant. It can be.
So that brings up an interesting question. Do you assume in your work throughout a single source of invariance, or do you also conceive of multiple sources of invariance? Like, there's a time invariance, but there's also the left
Yeah.
arm swing invariance
Yeah.
vector.
We are headed in that direction. Right now our investigations have
I
been
suspected
speaking
that
about
would be the answer. The goal is to be able to have
everything.
almost like a linear combination of known invariances that
Right. Right.
you can account for. But
Right. At this time, we have been playing it very carefully that let's take this one source of variable, let's see if that can be factored out. Let's see if we can get invariance to that. And we have had success in many different applications.
it sounds like you're further saying, though, that in the case of at least this motion capture type of a data set, that that maybe time becomes kind of a meta invariance that can account for multiple physical characteristics. Am I hearing that correctly in there?
It can. It's hard to write that out clearly, but it does. Like for instance, if you had like load bearing, if you are carrying a heavy bag on your back, it will have an interesting effect on the time series of your joints, which is not that easy to explain, but it will sort of stretch out certain phases of your movement and shrink certain phases of your movement. It does. So yeah, the stretchings and shrinkings of the time axis are the key to finding what that invariant is for that action.
And so, are there well-established benchmark data sets for these types of tasks, or are you rolling your own to explore these methods?
No, for motion capture, there are benchmark data sets. There are, Microsoft it used to have a RGBD data set. They go by the RGBD activity sort of, keywords, and there's a few out there. There's a few benchmark data sets out there. NTU has one, MSR is one, and sometimes even, the video data sets like HMDB have stick figures available through other methods like PoseNet, for instance. So yeah, there are well-established data sets that we experiment with.
And is the task that's posed by these data sets one of predicting the action that the
Right.
okay.
Right. It's activity classification and prediction by and large.
Yeah.
Right.
Okay. Okay.
Mhm.
And so what's the kind of state of the art for that kind of activity detection, and how does your method compare to it?
So most of the time series in the deep learning world, most time series things are either a combination of 1D CNNs or LSTM models. So depending upon the data set, the way our process goes is we say, let's find the latest benchmarks and we'll improve on those through these mathematical techniques. So a recent paper we did in CVPR 2019 used LSTMs as the benchmark data, the technique, and the datasets were NTU, 3D dataset, and a few others like that, motion capture. Uh, the tunable parameter in LSTMs is oftentimes the hidden layers. How many hidden units do you have? And of course, if you scroll through it, the numbers keep going better and better. The way we've done it is we kept things the same. We say, let's say it's 16 hidden units or 32 hidden units. Keep that the same. The only thing we'll change is add in this additional module that either disentangles the time warp function or adds in as a constraint, and numbers always go up. So in the way we thought about it, if my memory is right, the NTU RGBD dataset had like 80% roughly accuracy with a very fancy LSTM with 200 hidden units and stuff like that.
Mhm.
And we were able to improve it by 4 or 5 percentage points easy without any changes to anything, but just this additional constraint added in. So if you fine tune it more, sure, there's more things to be squeezed out. But we were able to consistently improve the performance of LSTMs by easy 5 percentage points, sometimes 6, 8 percentage points with no change, but a simple constraint on time warping. Yeah. So those are the kinds of results that we've been finding, which is if you rethink what the constraints should be through understanding the phenomena first, the payoffs are actually quite significant without any additional requirements on data or network architecture complexity or training strategies. They can all be very basic.
And so now we've talked about a couple of, very different types of problems. One kind of computer, a very visual type
Mhm.
of
Right.
task, and one that's more time series.
Absolutely.
To apply this to different settings, how much handcrafting needs to go into the loss functions and the different constraints that you're applying to the network?
That is where the big work is. So I think the pendulum is swinging to that level of handcrafting,
Yeah.
moving away from features to architectures and loss functions, right? That's where the pendulum is.
Yep.
And the amount of work that goes into handcrafting is a lot of, I would say, studying, basically,
Mhm.
understanding how these variables actually affect the observed data and try to express it in a way that is amenable to fusion with a deep net. The beauty is physics is not one way. Light is, there is no single model for expressing how light and surfaces interact. There's layers and layers and layers to it,
Yeah.
and you have to know all of that, or at least as much as you know, as much as you can learn. And then the handcrafting is where in this spectrum of sophistication do I stop
Mhm.
in a way that I actually have a pragmatic effect on performance without changing anything else. And that's where a lot of intuition is. You cannot get away from this intuitive exercise.
Mhm.
Despite all the progress of machine learning and deep learning, the networks are arguably both intuitive and highly unintuitive. I mean, some people have an insight about why a network works, but present it to someone else, it's mysterious. And the same thing is true of the loss functions business. Sometimes we can motivate it very easily through simple things like, well, yeah, cross entropy, mean square error makes sense. Physics is where some of the unintuitive stuff lies. It's That's where a lot of design thinking exists, and we are doing that. So yes, that's where much of the work is
Does that
understanding.
mean that when you approach the n plus one problem that's different from the ones that you've looked at previously, that you're starting from scratch, or are there some principles that give you a foothold when trying to apply this method to the new area? And if so, what are those principles?
The details, of course, have to be looked at from scratch, but the principles that we bring to the table are ideas of geometry and this idea that, look, whatever it is that you're observing, whatever is the raw space, that is not the space on which you want your analysis to occur. You want the analysis to occur in a space that is crumpled. And the generalizable knowledge that we bring to the table is how do we represent these crumpled spaces. And that's the mathematics of Riemannian geometry and topology, group theory. Those are all the new mathematics. I mean, it's not new mathematics at all. It's mathematics of the past 2 centuries. But in the realm of machine learning, that mathematics has not made its way in a systematic way. So that's the generalizable knowledge. We bring in group theory, geometry, differential geometry, topology. That's the way we think about it. But then the specifics, the problem specifics, have to be studied from scratch. But then that knowledge can often be expressed in the constraints of geometry and topology and group theory. And that's where we specialize. How do we take this domain-specific knowledge and look at it through the lens of groups and invariance? And that's a different kind of generalizable knowledge. It's really a way of thinking about phenomena rather than thinking about data.
And going back to your keynote, are there do you kind of take a step back and kind of apply this broadly to computer vision, machine learning, and do you kind of offer any thoughts for where this is all going? If not, just make some up. Where's this all going, Pavan?
So, data constrained scenarios, that's where this is all going. Machine learning with unconstrained amounts of training data is what the last 10 years were about. And we are finding that it's a nice goal, but there are no guarantees to be ever had. Even if you train it forever with as much amount of data that you got, if any mission critical deployment requires a guaranteed robustness of some kind, there is nothing to be given other than, yeah, this is what my numbers are on some data set. That's all you have.
And now, if I can just hit pause there, throughout our conversation, you've talked about constraints. You've talked about constraints on the network, and you've talked about constraints on loss functions. You've talked about constraints on architectures and not changing architectures, and those have implications on compute constraints. And that you haven't really explicitly talked about constraints on data. How does that fit into all this other stuff we've talked about?
The way I think about it is, if you don't have access to additional data, you get more bang for your buck by adding these additional constraints that we are talking about. If you have access to more data and you can collect as much as you want, you always should. That's undeniable. But it's becoming more and more clear that that's not where the future is headed. We are not able to keep training bigger and bigger. It's an unsustainable path. There is enough energy going in that direction anyway, whether or not we like it or I like it, but it's not a sustainable path of progress. It's smaller and smaller, diminishing returns for ever increasing resources.
So that's clear on the margins, but is part of your work trying to get at one shot, few shot types of problems, or no?
We are, that would be an extreme case. Yes. We are thinking more along the lines of, if I had to collect more data, can I first pause before collecting any more data and robustify what I've got with domain knowledge? That's the way I think about it.
Got it.
One shot and few shot, it's a whole different ball game. It's like the wild west of machine learning, and I wouldn't go that far yet. But will our methods be applicable? Sure, I don't see why not. But I wouldn't make big claims of getting one-shot performance, but it should definitely help. If not, make it more amenable to less training sets. Yeah.
Okay. So I interrupted you. You were talking about essentially that the data collection is always going to be expensive, and thinking about the problem space can provide these benefits.
Unfortunately, human in the loop can't go away. There is neural architecture search. Yes, again, will these succeed? They will succeed at developing some representations that get a job done. And when you layer in questions of interpretation, explanation, which everybody is talking about, I have a much simpler take on it, which is, if you don't have robustness to even simple physical variables, how will you even explain anything? I mean, if your classification shifts simply because I rotate a picture and you're asking me to explain it, I think you're asking the wrong question. If you're at least asking me, can you be robust slash invariant to simple things and then explain it to me, that's a more well-posed question. But these are premature questions to ask. And some colleagues of mine have gone so far to say repeatability. If your machine learning technique is not repeatable, and by that, things like this. Yeah, if I click this picture at a slightly different time of day, nothing's really changed except the time of day, and the decision has flipped. It's not, the process is not even repeatable. So don't even go to the extent of explaining a non-repeatable process or trying to interpret a non-repeatable process. Those are all questions that should come later. So if you think of repeatability, you do an experiment, you get the same result over and over again. uh, as far as the big things are controlled, machine learning hasn't yet delivered that even. So we're trying to bring in that level of robustness. I call it robustness slash invariance. Some people have called it repeatability, simple. And
Got
to
it.
me, repeatability sounds shinier, and it sounds like the stakes are much higher, but I'm happy to just call it invariance.
Well, Pavan, thanks so much for taking the time to share what you're up to and provide us some context for your CVPR keynote. Very cool stuff.
Thank you so much, Sam. This has been a pleasure, and you've been great. Thank you so much.
All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.